Alright, so today we'll be going over properties of cross sections. So, why is it important? Okay, so the stiffness and strength of a structural member depends upon a few things. What the material is, obviously, how much of it there is, how big this thing is, but also how it's arranged geometrically. So, if you have, if you have a bar that is, a square bar that's a particular cross area, that's a particular surface area when you cut off the end, that can have vastly different properties in how it resists bending or resists twisting versus, say, an I-beam that has the same cross section. That has the same area of its cross section. So, for example, I think it's fairly intuitive that this bar here is going to be stronger than this bar here. It's going to be better able to to hold axial loads. It's going to be better able to withstand shear force. It's going to be better able to withstand bending because it's bigger. Bigger is better. Well, depending on what you're doing, obviously. If you don't need the strength and you're just making it bigger for the sake of making it bigger, then it makes it heavier, and I'm sure your aerospace guys are definitely going to be having some issues with that. Something like this. I've got a rod versus a pipe. The rod will be stronger. The rod will be better able to withstand twisting or bending than this pipe here. That having been said, because there's more of it, we didn't cut a hole down the middle. That having been said, if we have, say, this wider but narrower pipe here, that maybe even that might have a smaller cross-sectional area than the rod does. That could, depending on exactly what ratios we're talking, it could still have a greater ability to, say, resist twisting than this one here. Just due to we're not as worried as much. Well, due to the fact that how it's arranged geometrically plays a role as well as just how much of it there is. So, a few cross sections that you might encounter. You'll see rectangles, you'll see boxes, circles, pipes, I-beams, T-beams, L-beams, U-beams. Sometimes you might see C-beams as well, which is basically just a U-beam on its side. Actually, you tend to see C-beams mentioned more often. But so one of the most important properties of cross-section is its centroid, the geometric center of a cross-section. If we're talking a homogeneous object, basically it's also the location of the center of gravity. So essentially, basically what you're saying is that if you take an object and you cut it in half through its centroid, kind of regardless of the angle at which you're cutting it at, you're still going to have half of the object on one side and half of the object on the other side. It's independent. The location of the centroid is independent of the orientation of the axis you're examining it on. So we calculate that based upon the concept of the first moment of area and the total area. So up here, the first moment of area is our XdA integrated, and the total area would be just dA integrated over the area. Okay, so let's assume that this grid that we're looking at here is basically zoomed in enough that we are kind of working at the individual little dA components there. And let's give it a certain shape here. So I don't know. Let's let's just do that box. Now the way we would go about doing that is essentially for the calculation of the for the calculation of the x bar, so the location of the centroid in the x-axis. That would be done by taking the integral of the x dA divided by the integral of dA all over the area. So the x portion, that's from the origin over to here. And the dA, that's just those tiny little blocks there. Multiply those together. So essentially, the reason that this will sometimes get called the first moment of area is because we are kind of basically for each of these individual little blocks here, we're basically kind of taking a moment about the y-axis here, where the moment that's being taken is basically that displacement there crossed with a moment, if we assume that of the area, so basically that crossed with kind of a vector going into the page of the area itself. So that is it. And then we basically, we zoomed in enough so that we can kind of just sum them up. So these tiny little squares, take that x, multiply it out, multiply it out, multiply it out. So all of these components here at the same distance from the y-axis, they'll all have the same x. So just multiply that. So you basically just add up how many of those there are, add up how many of the next one there are, the next one, the next one, the next one, so on and so forth. So increasing the x value, finding out how much area there is at that x value, and adding it up. So I think one thing that that can be seen fairly easily here is that you can, when you're taking the that the location of the x portion, it's independent of where it is in the y, right? So this will have the same x bar location as these two figures here will have the same x bar location, because basically we'll be adding this up and then dividing it by the total, adding this up and dividing it by the total. As long as the centroid of each of these individual ones is the same in x location, then we're talking the same x bar location. Obviously they'll have different y components. The actual centroid for this thing will be here, centroid for this thing will be right here. So they're at the same spot in the x, they're at a different spot in the y. And also each individual, basically the sum of let me see here. So you can basically determine that the centroid is going to be located if you take a structure and then add another structure to it. Let's say we do this. Now if we started off with this, it has a centroid right here, and then add to it these two components, and just looking at the x, actually here let's only worry about the x here. So I'm gonna crap. Okay, so only worrying about the X, I'm gonna this one centroid there, one centroid there, one centroid there. Basically, when you start out with this and add this second box here, you're going to shift the centroid for the overall object towards the centroid of the new box that was added, and the amount of that shift is basically going to be proportional to the relative size of the new object as a portion of the total of the original object. So basically, as you're adding these up, you're going to get a new XDA, combining those two, and then dividing by the new total area kind of will give you a new result that's shifted over a bit, proportional to how large this thing is compared to this thing here. So for example, 1, 2, 3. So from here to here, that's 3.5 squares. The total size of the object that was added, that's 8 squares. This one had the original one had 12 squares to begin with, so the new, discounting this thing here, of course, the new one is going to have 20 squares total. So just this section here, we're going to basically shift it over 3.5 squares times 8 over 20. So the new location for that is going to be just shy of that intersection there. And then we're adding a new box. Again, we can basically do the same thing. From here to the centroid of this object, we have, let's see, 1, 2, 3, 4, 5, 6, 6.6 squares. This one is the size of this new object. That's 4 by 5, so that's 20 squares total there. So again, that's going to be basically equal to the size of the overall, the initial object. So if we got 6.5 from here to here, and this thing added here is half of the total size of the new object. Once we add this section here, then we get another shift over that'll be basically 6.6 plus divided by 2. So we're shifting over 1, 2, 3, and 0.3. So the new final center of gravity, which I'm going to denote in green there, that'll be about there. So adding mass to an object shifts the center of gravity towards that object. The converse works too. If you have an existing object and you carve a section out of it, then you get a shift away from the previous center of gravity, and that'll be the new center of gravity will be located on the line of action from the center of gravity of the removed section and the center of gravity of the original section, but it'll be moving away from the removed section, and the amount that it moves away is directly proportional to the distance between those two things and the ratio of the amount that was removed and the original object. So yeah, we don't necessarily need to be integrating all the time. We can break stuff up into the sum of its terms and work with simpler shapes. So finding the various moments of area for the objects in question, adding everything up, and then just dividing by the total area. Which again, when we're removing objects, kind of works out to the same thing as this entire thing minus that, instead of trying to figure out what, the centroid for this section minus that would be directly, which would be just a pain in the ass. So get a shift proportionate to the area divided by the new total area. And here's just an example of how we would get shifts based upon removals. So if we had this object here that had an original centroid and we drill a hole in it here, we're going to get a shift. The new centroid is going to be located along this line from here to here, but it's going to be away instead of shifting towards. So some properties that are quite useful in determining the location of centroids. If the thing is symmetrical about any axis, the centroid is located on that axis. So if it has more than one axis of symmetry, then the centroid is located at the intersection of those axes. So you can have lots of shapes that have different axes of symmetry varying from, zero to infinity. Circle has infinity axes of symmetry.